So good evening, everyone. So we'll start today's session. So can you able to see my screen? Okay. So in the last class, we have discussed about how to parallelize using blocks and how to parallelize using threads and all. So we'll see something about what is SM and how the blocks are represented. So what is that? Where is th- where is there? Where the thread is located? Everything now. So here in this particular diagram, this is a CUDA programming model. Okay, so SM means stream of multiprocessors. So here some n number of stream multiprocessors are available. Each and every stream multiprocessor is having its own registers and cache and other DRAM. So they can able to the stream multiprocessor can share the DRAM. It's a global memory for all the stream multiprocessor. So it is having their own registers and the L1 cache. L2 cache is common for all the stream multiprocessors. And here the L2 cache and DRAM both are read only. Okay. So here it is a CUDA kernel and thread hierarchy. So here it does how the threads are executed on the GPU. Okay. So how the kernel function is executed on GPU. So here within the box, it shows the kernel function. So only the kernel function is having the thread ID and block ID, everything. And so how many number of threads you have specified in the kernel launch, based on that, the CUDA threads have been utilized for executing the kernel program. Okay. Um, so here, the parallel portion means the kernel program. Okay. So only the kernel program is parallelized in GPU. So here, executed k times in parallel by k different CUDA threads, as opposed to only one time like regular C and C++ function. So what it means is, normally if you have written any functions in C or C++ programming languages, what happens is, if you called a function once, that function is executed only once. Okay, so we are all know that. So in GPU programming, based on the kernel launch, how many number of blocks and threads you have given, based on that, that particular program is multiplied. That is, the kernel program is multiplied, executed multiple times. The kernel program is executed multiple times. Okay, so here, what is block is, we can say a group of thread is called CUDA block. Okay, a block contains more than one threads. Each and every block contains more than one threads. And in any GPU, it will be having either you can say k-1 or k-1 blocks. So all the blocks are combined together, which is called as grid. Okay. So we have to remember these three words. One is grid, another one is block, another one is thread. Thread is inside the block. Grid is the collection of blocks. Okay. So CUDA blocks are grouped into a grid. A kernel is executed as a grid of blocks of threads. Okay. So in the grid of blocks, we can execute the CUDA kernel, so with the help of threads. Okay. And so we can say uh, each and every streaming multiprocessor is a CUDA block. Okay, so I think you people can understood easily. So here from this diagram, we can say that small green boxes are called as stream of multiprocessor, and this stream of multiprocessor is called as block. Inside the block, we are having a number of cores. We'll see how many number of maximum allowable cores or maximum allowable threads. So everything we can see now. So here, each and every core will have a thread. Okay. So each core is mapped to a thread. And so one SM can run several concurrent CUDA blocks depending on the resources needed by the CUDA blocks. Each kernel is executed on one device, and CUDA supports running multiple kernels on a device at one time. Okay, each and every kernel so will be executed on one device, and CUDA supports running multiple kernels on a device. I think you people can understand this particular statement. And so if you have written one kernel program, that is CUDA program, so that kernel program will be executed on one device, only one device. Device means here it is GPU. And also the CUDA API can support multiple kernel programs on a device. Already we have seen some examples which is having multiple kernel programs. Okay. So if you have written multiple kernel programs in a single CUDA program, that can be executed on a device at one time. See here, this is a kernel execution and mapping on hardware resources. So actually, each and every thread is mapped with the CUDA core. And CUDA thread blocks contain, we can say CUDA thread block is a streaming multiprocessor. One streaming multiprocessor is related to one thread block. Okay. So, and CUDA kernel grid, and the GPU consists of a number of blocks. Okay. So that is called CUDA kernel block. Okay. Hope you have understood this one. And okay. So here in CUDA API, you can define 3D variables for both threads and blocks. Okay. Already in last class, we have seen for thread programs, we are having thread idx.x, and block program, we are having block idx.x. Okay. So instead of giving x, you can have 3D variable in the sense we can use x, y, and z. And here the thread is indexed with the help of thread idx. Okay, so the indexing is happen automatically. There is no need to increment or decrement like our C program. Okay. So here also blocks are indexed with the help of block IDX. Threads are indexed with the help of thread IDX. So it is the variable which is available in CUDA. So also the blocks are indexed with the help of block IDX. It is also the variable available in CUDA. Okay. So some important points are there. And so number of threads per block is limited to 1024. Okay. So in each and every block contains 1024 threads. Okay. You can say 1024 cores are there. So in each and every, each core is mapped with one thread. And one more thing is there, all threads. So, okay, we can also synchronize all the threads within the block with the help of sync threads, which is available in CUDA. So, _sync threads. And okay, all threads in the block must wait before anyone can proceed with the help of the sync threads. You can synchronize the threads. Okay, so we all know that the usage of triple angle brackets. So it is very much used for calling the kernel program from host. Okay. So again, the programming model, the other name for programming model, it is called memory hierarchy. Okay. So here the L2 cache and global memory, that is DRAM, is common to all the streaming multiprocessor. It is shared among all the multiprocessor. And each and every multiprocessor having their own registers at L1 cache. Okay. You know that what is a register. Okay. So the registers are here in GPU, the registers are private to each thread. And so once one register is assigned to one thread, which is not visible to the other thread. So that means each and every thread can be executed in their own way. Okay, that is individually. And you know that what is L1 cache? That this L1 cache is shared memory, which is shared among all the threads in a single SM, streaming multiprocessor. And so here it is having the instruction cache, constant memory, textual memory, auto cache. So everything is there. Already we have discussed L2 cache and global memory. It is shared among all the streaming multiprocessor. And so every thread in that CUDA can access this memory, that L2 and global. So some of the latest NVIDIA GPUs are A100 and V100. So in A100, it is having L2 cache size of 40 MB, and but the V100 is previous to A100, so it is having 6 MB L2 cache. Okay, so global memory, you know that it's a frame buffer size because there is no main memory in GPU. Okay, so next we'll see about how we can use threads and blocks in a CUDA program. So I have given one textbook in chat. Okay, it is a very good book for studying CUDA program. Okay, so you can go on through. So we'll move to the next topic. So using threads and blocks. So already we have seen some of the programs using how to use many blocks with one thread and one block with many threads. Okay, so in threads program we have used only one block with many threads. So in a blocks only program we have used many blocks with each block will be using only one thread. So here also in threads and blocks, we are combining both thread and blocks. So here our example is vector addition. And so here the important thing is how the data is indexed in threads and blocks. Okay. So through this diagram, we can easily understood. So in the bottom portion of the presentation, I have given one diagram, one formula. So how the index is calculated. Okay, we are combining both threads and blocks. So you have to multiply block with the width m. Okay, so width means number of threads in a block. So width means number of threads in a block. It is here. So using 8 threads per block. Here in our example, we are having 8 threads per block. Okay. So you have to multiply the block idx.x index with number of threads in a block. That will be added with the thread idx.x index. Okay. So here in this diagram, we are having 1, 2, 3, 4. 4 blocks. Okay, that is indexed by 0 to 3, like in our array. So we are having each block contains 8 threads, that is indexed from 0 to 7. Okay, it occupies the sequential memory. Okay. So next is I need to get a data from second block, fifth thread. Okay, second block, fifth thread. Okay, that is the problem given here. So what you have to do is you have to multiply this block with the number of threads in a block, 8, 2 into 8. That is added with the uh, uh, thread IDX ID. Okay, that we have given us 5. Okay, that is 21. Okay, so it is denoted by red color here. So thread IDX, the index for second block, fifth thread is 21. Likewise, the data is calculated. Okay, so can you able to follow me? Can you able to follow me? I didn't receive any messages.
Yes, ma'am, we are able to follow.
Okay, okay. Okay. So in this way, the index is calculated for combining threads and blocks. Okay, so already the statement is here. Okay, so the variables for number of threads in a block is block dimension, that is block DAM. Okay, number of threads in a block is block DAM. Okay, so the statement is written like that: index equal to thread IDX dot x plus block IDX dot x into block DAM dot x. Okay, so while performing vector addition, you can write the kernel program in this way. Okay, so either you assign this formula value into an index and put it here. So otherwise, directly you can also write. Okay, like our block IDX program or thread only program. Okay, so this is a kernel program for that. Okay, so again the same thing. Okay, parallel addition for number of blocks and threads. So here the same kernel program. Okay, so again we have to define threads per block. So here the threads per block is defined as 5 12. Okay, so and hash define n of some value is multiplied and some bigger value has been taken. So already you know that what you have to do. For addition, we need 3 variables, 2 for one for result and 2 for the value to be added. So first we have to allocate the memory for CPU, then we have to allocate memory for GPU. So after that, what you have to do is we have to here we are declared. After that, we have to allocate memory space with the help of CUDA MLR. So also we are allocating memory for A and B in CPU, and also C, no problem. The results has to be transferred from GPU to CPU and it has to be stored there. So directly I have given the values A equal to 2 and B equal to 7. So you can use scanf in Colab, no problem. It will be working. So I have checked. And so after that, what you have to do is you have to copy both the values of A and B from host to device. That is CPU to GPU. That has happened there here. So next we have to launch the kernel and n. We have given some bigger value n. So that has to be divided by the thread per block. Okay. So if you have defined some value that is called number of threads per block, that has to be divided by the number of blocks. Okay, so that has to be done. Then the values have passed. After that, what happens? The result is stored in dev C, that is copied from device to host, then it is printed here. The free is freeing the memory of CPU. This is for freeing the memory of GPU. So I'll paste the code on chat. Just try to execute. In the meantime, I will also execute. Okay. I'll paste it here. Also copy that. These two statements are missed here. This error. I missed some code. Uh, okay, it is executed. Next. Okay, sum equal to 9. So anyone executed? So while pasting, I have missed some of the lines. I'll paste it again. This is the first part. Where I have to copy the B. First copy of C. And the remaining thing. This is a complete program. Okay. So anyone executed? No. Okay. So we'll execute later. So I'll move to the next one. So the same thing as explained here. We'll move on to the next one. The previous slide I will explain later. So after some time. And so another one program. Okay. So in this one, you have noted one more thing. So I didn't tell. So the number is divided by thread per block, comma, threads per block. Okay, so that is already given, 5 total. So sometimes it may have, each block will be having 32 threads and all. Okay, so but even though only 32 threads are there, so you can give any number of threads. It's not a problem. So it will be taken care of by the GPU. So again, what clearly said is you have to give some bigger number of value for number of threads too in the kernel while calling the or while launching the kernel. Okay, you shouldn't give very small numbers. Okay, that's again one more thing. And the next program is so we are so it's again using thread program thread. Here we are using some character array. Okay, so in the main program we are having one GPU array and one CPU array. So on the CPU, okay, what are the variable you have declared there in the CPU? You should declare there in GPU. Okay, so that's the main thing. So here in CPU array, we have given some characters. So what these characters will do is it will display some hello world. Okay, and again one pointer. for GPU array. So next is while storing the character array, what happens is after end of the character will be printed along with the any character array. Okay. So here for allocating memory space in GPU. So what is the string length of CPU array? The value is there in the CPU array. So you have taken the length of that CPU array and add 1. Okay. So that is the size we are going to allocate there in GPU. So one is for that is end of the string. And next, what we are doing is we are copying this particular value, that is character array value, into device. Okay. So then we are calling that is launching kernel 1 comma 32 threads. So here what happens is um, so we have given the GPU array and the what about the length of that particular string? Okay. So then you can either you can give CUDA device synchronize or not. Okay. So in the case you try to run. Okay. Once it is completed, what we are doing is you are copying it from device to host. Okay. So coming back to the kernel, so we are passing two values. Okay, one is the character array and the array length. So that's why while launching, we are also giving two values. Okay, both the GPU arrays and the length of the character array. So here we are using thread IDX. Okay, so we have given some threads, and if ID is less than array length. Okay, so the ID value is okay. Thread IDX is assigned to ID. ID with length, ID is less than array length. Okay, what you are doing is you are incrementing array of ID. Okay, so after that you are printing CPU array. So we'll see what happens. Already I have executed this one. Okay. So again, one more thing is in that program, what I have given us, I am passing string length of CPU array plus 1. Okay. What's the need for this plus 1 is for end of the string character. So actually that is not needed while printing. So while doing here, I didn't given that one. Okay. So already I have executed this one, and there is some warning. It's not okay. So it is executed as hello world. Okay. So this for this will be getting hello world. Okay. So I'll paste the program there in chat. You can try to execute that one. Sorry. Okay, okay. So, but it is working in Colab. Okay, but it is okay. CUDA up to CUDA device synchronize. After that, you are having some more things. Sorry. This is a complete program. So from this, you could understood how can you declare arrays and how can character arrays with the help of character array, how can you allocate memory space, everything. Okay. So actually, this one is not needed. Okay. That's why I have pasted the program there in Colab. Okay. So I have executed some more programs there in. We'll see the matrix multiplication in the next class. Okay. So we'll see. I have done some of the programs using one-dimensional matrix. Okay. So here, after that, we'll move to the next one. Quickly, I gone through this one-dimensional matrix. So here in one-dimensional matrix, in the first program, I have used the block ADX. Okay. So it's an addition program, and I am using only the block ADX. So we are having three arrays. Okay. So one is X, Y, and Z. Okay. So this is the addition one, a statement for adding two matrices. So here in CPU, I have declared three arrays. Okay. So the corresponding GPUs are star D, star E, and star F. So then I have used for loop for getting values for the first array and the second array. So then I am allocating memory on GPU. So in each and every array, we are having 6 integer values. So I have multiplied size of int with 6 for all this. Okay. So then we have to cudaMemcpy. Here also, otherwise, what you have to do is in some other variable, you multiply everything and you could use that variable here. So I directly multiplied those things here and copied all the values to GPU 2. Okay. So I have launched the kernel with only one thread. So I am using 6 blocks. So I am passing the arrays here. And so once it is done, the everything is copied back to CPU. So now we are having everything there in CPU in CR5. So that is printed here. Okay. So do you want me to execute this one? I'll execute this one alone. Okay, so I have saved and compiled. So you'll be getting like this. Just a minute. Okay. Game. I'm giving. Okay, so the two arrays have been added. Okay, this is a one-dimensional array. So likewise, here instead of using block, I'm using thread. Okay, all the remaining things are same here. But while calling, so I am using only one block because it has thread IDX. It is only using only thread. So I am using only one block and having 6 threads. Okay, so all the remaining things are same. Okay, same way it will be executed. So in single dimensional array, so I'm using both block ADX and thread ADX. Okay, so you have to multiply block ADX with block dim. Okay, you have to multiply block ADX with the block dimension and added with the thread ADX. Okay, so that's a different thing. So all the remaining are same. So here I have used 2 blocks and the 3 threads. Okay, each block using 3 threads. Here. So the number of blocks and number of threads usage will be based on your problem. Okay. So sometimes if you have used a large number of blocks, it takes more time, and you have to randomly give, and you have to get how many number of blocks and how many number of threads will give the correct value for the what how speed of the GPU is. Okay. So again the same thing, same values I have given and is displayed. Okay, I'll share the program so you execute. So I quickly gone through another one program, that is matrix squaring. So you square the values in a matrix. Okay, very simple. So this is a CPU program. Okay, CPU, what is called the code of matrix squaring. Okay, so I am not executing, simply explaining. So here the n value is given as 64, and so all the values are defined as unsigned values. So here you can use both blocks and threads. Okay, this is a one version of matrix squaring. Okay, so you do execute the program and find out how long it takes to execute. Okay, and there is two for loops for taking each and every values. So this is the same statement we are using there in the CPU. Okay, this is a one version. So this is a kernel program alone. All the remaining things are same in for all the programs. Okay, this is a matrix squaring version 2. Okay, so what happens here is the I value and j value is divided by the matrix size. Okay, size n. So then after that, it is calculated again using the same statement. You can simply check what happens while executing these three programs. Okay, this is a CPU one, the GPU version one, and this is a GPU version 2. Okay. So here the GPU computation hierarchy. So already I have explained in different diagram. GPU has hundreds and thousands of cores, and it is having stream of multiprocessors. Okay, in 10,000s. So each stream is, we can say it is a block. At max 1024 threads are there. Okay, and wrap threads are there. Okay, so this is a only one thread. Here you are having 32. Okay, so warp is a set of 32 threads within the thread block. All the threads in the warp execute the same instruction. Okay, so all the 32 threads execute same instruction. And how these threads are selected is, these threads are selected serially by the streaming multiprocessor. Okay, so and the next concept is dot product. So already we have seen vector addition. So you know what is a dot product? It's something different from vector addition. And here is one example. So we are having values A0, A1, A2, A3, and B0, B1, B2, B3. So what happens in the dot product is A0 is multiplied with B0 and A1 is multiplied with B1, A2, B2, and A3, B3. Then after multiplication, you add all those things. This is the dot products. So many of you know that. Okay. So how can we calculate this dot product using GPU? And so here in this, we are having A, B, and C. Okay, three values. We are passing all the values in the kernel program, kernel function. So next we are finding one intermediate value. That is, what you are doing is A naught, B naught is multiplied. A1, B1 is multiplied. That happens here. Okay, with the help of thread IDX. Okay, so A of thread IDX multiplied by B of thread IDX. So this particular multiplication is done here. Okay, so here this end I will be small only, and next is you have to add all those things. Okay, And okay. So here, how we are sharing data between threads. Already we have seen that there is a shared memory available. The help of shared memory. So data is shared among different threads. Okay, there is one CUDA keyword is available that is called underscore underscore shared underscore underscore. That is a CUDA keyword available. So you can use this one for managing the cache, which is there in the blocks or threads. Okay. So this is a parallel product. So here what happens is we are having a number of elements that is temp of n. Okay. So it is again considered as thread. Okay. So we are sharing this temp. Okay. So here what we have to write as temp of thread idx dot x equal to a of thread idx dot x multiplied by b of thread idx dot x. Okay. A naught into B naught. Okay, that happens here. So after that, what happens is they are doing pairwise products. Okay. So then everything is done with the help of thread 0. Okay. So you're having thread 0, thread 1, thread 2, thread 3, etc. So how many variables are there? Based on that, the thread index will be increased. So once everything is done, so what you have to do is with the help of thread 0, so you are summing all the values. That is here. Okay, you are calculating A0, B0, A1, B1, A2, B2, A3, B3. Okay, so once done everything, okay, with the help of thread 0 contains A0, B0. Okay, so all the remaining threads values will be added together in thread 0. So that is written like this. Okay. So again, it is shared. Okay. Already we have seen that the each and every thread it is if you have to explicitly give shared. Otherwise, the data won't be shared among the threads. Okay. That's why we have to give the shared keyword here. Okay. Then you add everything. Then that will be stored there in star C. So in parallel dot product, what we are doing is we are performing pairwise multiplication. So shared memory stores each thread's results. Okay, that is stored in shared memory. So after that, you have to sum these pairwise products from a single thread. Okay. So there is again some more problem is there with the here in what is called dot product. Okay. So can you able to identify what happens? We are sharing and adding everything happens. So what else we have to do? Any idea? So can you able to follow this dot product? Everybody is asking. Yes, yes. Okay. So then what else we need for performing dot product? Initially we have multiplied. After that, if you have given like this, int temp equal to a of thread idx dot x into b of thread idx dot x, it won't help. Okay, so it will be having only one value of a dot b dot, otherwise a1 b1, a2 b2, like that. Okay, so that's why we have used the shared memory concept here, because the threads values are not visible to other blocks running in parallel. Okay, that's the reason. So this particular block 0 is having some threads, it shares the memory. So again, it is having shared memory. Block 2 is having some shared memory. So this block 1 shared memory and block 2 shared memory is not shared. That's why we are using shared keyword explicitly. So here we are using different threads, okay, and for these threads we have to synchronize all the threads, okay. So then only we can able to correctly get the dot product output for performing while performing dot product, okay. So we have to synchronize. We'll see the synchronization part in the next class, okay. So any other doubt? So in matrix squaring, I didn't explain how to square the matrix values. So you just gone through. So I have only explained what happens in block IDX and thread IDX and block dimension and all. So in today's class, what we have seen is we have seen something related with what is a block, what is streaming multiprocessor, what is called threads, and how the threads are sharing the data. So what about the DRAM in GPU and everything? So how many threads are there? How many blocks are there? And what is called core? What is the name for block? What is the name for streaming multiprocessor? So all the things we have seen, and also we have seen threads and blocks. Next, how we can write one-dimensional matrix addition multiplication using threads and blocks. Okay, everything, and also dot product. So while using the synchronized CUDA keyword will be, we can see tomorrow. Okay. So any other doubts you can ask. So Ram Prasad is asking, can you please explain atomic add in CUDA? I don't think what you are meaning for atomic add. I didn't understand what is atomic add. So whether it is a kernel or a function in CUDA, so it's a function in CUDA. Oh, okay, okay. So, while seeing the CUDA function, we can see what is atomic add, how can we use all those things. Okay. So the next topic is we have to see how we can use the dimensions. Okay, 2 dimensions or 3 dimensions. So how we can write 2 dimensional code, 3 dimensional code. So everything. The next class. Anything else? So choosing blocks and threads based on problem size. Okay, so you choose block and threads. So initially we have to give some randomly. So after that you can get an idea of giving number of blocks and threads. But even if you have given some high number of blocks and threads, it's not a problem. But sometimes it may take some very long time for its execution. So if you are having some large amount of data, so in all our example programs, we are using very small amount of data. We are not using a very huge amount of data. So mainly our GPU is for data parallelism. So if you are having huge amount of data, then only you go with some GPU computation. So, and you are asking the question like how we can know that whether the GPU is fully utilized as per blocks and threads. I don't mean that whether we are going to fully utilize GPU or not. Okay. So how much cores we needed, how much blocks and threads needed for that problem, that is enough. So there are different programming options are there available. So if any computers are there, computers or workstations or servers are having more than one GPU, so you can also allocate, use more than one GPU for a single problem. And if you are having only one GPU, you can use only one GPU for that your problem. In some case, one of my friend has done a research on. We are having L1 cache in each and every block, that is streaming multiprocessor. So for speed of the calculations or executions, what she has done is she has stored the data. Okay, minimal amount of data can be stored in L1 cache, but she has stored the minimal amount of data in L1 cache and executed. Okay, for faster execution. So instead of using fully GPU, so we need some execution has to be happen very quickly. For that only we are going with GPU. Am I right? Okay, thank you. So, any other doubts? So, already in the initially, I have pasted one textbook by Jason Sanders and Edward Carr. So, this is a very good textbook for studying CUDA programming. Along with two textbooks that is there in lecture 2 references. Okay. So, okay, thank you. We'll continue the dot product, everything in the synchronization part next class and also the dimensions in the next class. Thank you once again.
Thank you, ma'am.
Thank you.
Thank you, ma'am.
Thank you, ma'am.
Thank you.